Acid-base titration. If you will notice, you don't need to turn there if you trust me, like I trust you. If you look at the last paragraph on 340, it says, notice, and it's referring to this whole section on titrations, notice that there is absolutely nothing new to learn to understand titrations. That assumes, of course, that you already know everything up to this point, right? So if you've been following along in the book, like we have, chapters 1 through now chapter 9, and you've worked through to the point where we are in chapter 9, module 9, acid-base titrations, there's nothing new here to learn. There is, however, a different application of what we've already learned. And so yesterday I gave a brief introduction to titrations. Today I would like to walk through how to solve a titration problem, and then at the end of today, and if not today, tomorrow, actually watch a video of a titration. It's not as amazing, I know, as all of us standing around our own titration setup, but I want you to at least see and be able to visualize what a titration actually is. Okay. So just like on the dilution problems, where we can sit here and do the math on the board and have, M1 V1 equals M2 V2, we can solve for a V1, and we're all done. We've got V1 equals a certain volume. The question says, what would you do? And I encouraged the folks yesterday that stayed for tutoring that when it says, what would you do, the answer to what would you do is not V1 equals 0.25 milliliters. No. Now that you have that information, what do you do with it? And the standard response to that is, well, generally you're doing a problem where they say you have a stock solution of something and you want to make a certain volume of a certain molarity. What do you do? In that case, you would solve for the first volume, and your reply to the question would be something along these lines. I would take so many milliliters of the stock solution, place it in a container, and fill it until it has a volume of whatever my V2 was, and then it will have a molarity of M2. That's pretty much the standard answer for taking a stock and creating a new solution. So one part of that is doing the math, and the other part is understanding what's taking place. In that dilution equation problems, you pretty much do the math first and then understand what's taking place. For titration, you need to kind of understand what's taking place and then do the math to solve it. But I figured out last night and on the way in this morning how we can actually use what I've been calling the solution path, or the H diagram underneath the reaction equation, to solve a titration. So maybe actually showing you how we're solving it mathematically and then watching how we do it practically. Those two things will come together, and you'll recognize that, hey, there is really nothing new here that we haven't learned already. It's just how do we understand it in maybe a slightly different way. So what I'm going to ask that we do is, first of all, look at what a titration is. It says by the definition on page 336 that a titration is the process of slowly reacting a base of unknown concentration with an acid of a known concentration, or vice versa, until just enough acid has been added to react with all the base. This process determines the concentration of the unknown acid or base. I gave a preview to this yesterday, and here's a real rough drawing on the board of what it might actually look like. Let's say that we had an acid in a beaker, and we had a base in a titration tube. And what this allows us to do, there's usually a little mechanism here that allows us to turn it, and we can put drip, drip, drip into the acid. And hopefully by now you'll see that this is an acid with the base being added to it. As each drop of base hits acid, it reacts with the acid and neutralizes, whether it's a covalent base to produce ions or whether it's an ionic base to produce water and a salt. That process is taking place. There's excess acid and we're dripping in base in this example. It could equally be an acid in here and a base in here. The same reaction is taking place. That whenever a drop of whatever is acidic meets a drop of whatever is basic, they're going to react according to the reaction equation for those two chemicals. And when they do, they're neutralized. If we put an indicator in here that tells us, that indicates base. Remember, we've got indicators, some of them are one color when they're acidic, another color when they're basic. Sometimes they're clear until the solution becomes acidic or basic, and then they switch. So they give us, as human beings, a visual way of knowing when the perfect match point has been crossed. When we suddenly have an acidic solution that suddenly becomes basic. How would it become basic? Because more base is put into the acid than it can neutralize. As we're dripping base into the acid, this concentration of acid in that volume is becoming less and less and less and less. And at some point, a molecule of base that's added no longer has a molecule of acid to react with because all the acid has been neutralized. At that point, though it might be microscopically, a razor-thin fraction, technically this becomes basic because there's more base than acid. There may be no acid and just one molecule of base, but the net is a base, right? So what we're trying to do is find that point where, according to the reaction equation, we have exactly the same number of moles of acid that is required to base according to stoichiometry. There's that word again. Stoichiometry. Maybe actually working the problem and seeing it on the board and then going back to this idea of perfectly matching the amount of acid as required to the amount of base to get that point. Right now you just kind of have to believe that we can figure out where that point is. Let's go to On Your Own 910 and use that as our example to kind of understand this whole process of titration. This whole process of perfectly matching the amount of acid needed to the amount of base in order to perfectly neutralize, which will be according to the reaction equation for those two chemicals. So it says that we have, and what I would encourage you to do, when you look at read a problem, you recognize, hey, this is going to be a titration. Just go back and work first with the formula, and then go back and work with the particulars that you're given. So on your own 910, it says 125 milliliters, particular, we can hold off on that for a minute, of nitric acid, HNO3. So we're going to react HNO3, the nitric acid, is titrated. Again, there's our cue. It's a titration problem. Why? It's titrated. What does it mean by it's titrated? We do this. We drip them to find the match point. Okay. So we have nitric acid is titrated against magnesium hydroxide. So now we're not given the formula for magnesium hydroxide. We have to come up with it. But since we've been through Module 4, 5, 6, 7, 8, and now 9, we know how to figure out what magnesium hydroxide would be, right? It's going to be some combination of magnesium with hydroxides. Is this covalent or ionic? It's ionic, right? Okay. Now, is this formula for the molecule correct? Magnesium hydroxide. Look over magnesium. As a cation, what charge does it take on? +2. What's hydroxide? -1. So what must the ratio be between the two? 2 to 1. 2 hydroxides for every 1 magnesium. So I'm going to do that by putting it there. Okay? So nitric acid and magnesium hydroxide. Going to titrate those two things. So we don't need any more information from the problem. We have a little bit of work to do with this. This is an acid and an ionic base that react to produce what? Water and a salt. Now, I'm going to leave a line for the salt for now. To make the water, I need to match what? I have to have in the right proportion the... Right. Are the hydrogens and hydroxides equal in number as currently written?
Yes.
No.
No.
We've got 1 hydrogen and 2 hydroxides, right? So what do I need, Ray?
One more hydrogen.
Another hydrogen. I get that by...
Adding, we'll put a 2 in front of it.
Right. I can only change coefficients, don't change subscripts. Some of you are still doing that. Don't change subscripts, only change the coefficient. So what I'm saying here is I need 2 acid molecules to combine with every 1 base molecule. Why? Because the base has 2 hydroxides in it, and I need 2 hydrogens to match up with those 2 hydroxide. And that will produce, well, we got 2 and 2 to produce 2, right? And now we're left with the salt. What's the salt going to be? Well, it's going to be the metal from the base and the leftover portion from the acid. So it's going to be magnesium titrate. Right, because I've got 2 and 1. Remember this we set at a +2 charge? Each one of these has a -1 charge, and we need 2 of them there, and we have 2 of them. So that's our balanced reaction equation for nitric acid and magnesium hydroxide. What are the 2 molecules, though, that are in play, that are in question here? The question is usually going to be, for titration, the relationship between the acid and the base on the reactant side. They're not asking how much of this you can make. They're getting to how much of this you need to balance this to get the perfect. So that there's not going to be any leftover acid on this side because we used up all the acid. And there's not going to be an extra base because we used up all the base. We're shooting for this point, and we know that we can never get it perfectly. But we're actually shooting for this point where we have the exact number of molecules of acid that are required with the base to get only the products and no excess of anything. That's what titration is driving toward. So, for every 2 molecules, we need 1 molecule. For every 2 moles of molecules, we need 1 mole of this molecule. See that by stoichiometry? That's the relationship. So we're relating the acid and the base. So what I'm going to do right now is just go ahead and set up my solution pathway by using the H, like I've taught you already. Remember, we could go through, if we wanted to, and fill in all these different things. This would be mass, and this coming down, depending upon the direction, we know we've got mass, we've got the molar mass, and this is moles, and this is molarity, and this is the volume, right? Same thing on the other side. Mass, molar mass, moles, molarity, and volume. This first half we learned with straight stoichiometry. If I've got this many moles, how many of these do I need? Well, if we're just talking moles to moles based upon this reaction equation, we can see the relationship there is 2 to 1, right? So if we're converting moles, for every 2 moles of the acid, we only need 1 mole of the base. Okay? Now, what does this problem, now we go back, now that we've got this basic idea set up for the solution diagram, let's go back to the problem and find out what are we given. And maybe replace on the diagram the things that we're given, and then identify what we're asked for, and then drive the pathway to the solution. It says that we're given 125 milliliters of nitric acid. 125 milliliters. Now again, I want to encourage you to convert that automatically into liters, because when we work with molarity, molarity is going to be given in moles per liter. So to make sure you're working with the right volumes, convert the volumes that you're given to liters. 125 milliliters is 0.125 liters. It says we have 0.125 liters of nitric acid. So all the information down here deals with the nitric acid, and all the information down here deals with the magnesium hydroxide. 125 milliliters of nitric acid with an unknown concentration. Molarity is don't know. Is titrated against magnesium hydroxide with a concentration of 2.3 molar. If 35.4 milliliters of base is required, this is my base, right? 35.4 milliliters is 0.0354 liters. You with me on that? I just 35.4, 1, 2, 3, moved it over, 3, and changed the units to liters. If my magnesium hydroxide has that molarity and I use that much of it, what is the concentration of the acid? So see, according to our solution pathway, I've been given this, I've been given this. I know this based upon the reaction equation. I've been asked for the molarity, and I know the volume. Now, up until this point, we've generally been given a solution pathway that ends at usually ends at mass, right? Even the one we've done so far in this chapter, we started with the volume and a molarity to figure out moles, drive moles to moles, and then go moles to mass. This is just slightly different in that we're asked for a piece of information that's along the pathway, but not at the end of the pathway. Let's stop for a minute and think about what we're going to do. Where are we going to start at on the solution pathway here? We start with what was known and given and drive toward what's unknown. Unknown's on this side, so I would suggest we're probably going to start over here, right? Because I've been given a volume and a molarity, and what can I compute from those two numbers? Well, if I move from volume to molarity going in this direction, I'm going up, so I'm going to multiply, right? I'm going to multiply these two things together. So 0.0354 liters times 2.3 molarity, which is a moles per liter, is going to tell me how many moles of magnesium hydroxide I've used. And that is 0.081. If I have a 2.3 molar solution and I have 0.0354 liters of that solution, in that solution I have 0.081 moles of that molecule, magnesium hydroxide. I've taken volume times molarity to calculate the number of moles. Okay? Now, given that and following the solution pathway, I can either drive towards mass, but is it going to take me anywhere that leads me to my required answer? No. I need to move over here towards what's unknown that I've been asked for. So I need to cross over from here to here, and I do that by following the stoichiometric bridge across. How do I relate the moles of the base to the moles of the acid? Well, it's according to the stoichiometric coefficients, this conversion factor. As I move from right to left, I'm going in this direction, my conversion factor is going to be 2. You see that? So for every 0.81 moles of base, how many moles of acid do I need? .162, is that right? Okay. So what am I saying here? Well, for every 1 mole, I need 2 moles. And since I actually used 0.081 moles, that neutralized 0.162 moles of my acid. How do I know? Well, I know that I have that many moles because I have that many moles per liter and have that many liters. Multiply them together, that tells me how many moles. That relates to this number of moles based upon a 2-to-1 relationship between the acid and the base. Okay, so now I'm here on the pathway. I've gone from here, up, across, and again, normally from here we might have gone up before, but now we actually have to drive back down because we're working with 2 solutions with different molarities. I have 0.162 moles, and I know that my volume was 0.125 liters. So what's the molarity? Remember, what is molarity? By definition, molarity is the number of moles per the number of liters, right? That's what this piece of information is. The piece of information that I've been asked for is what is the molarity of that solution. Whatever it is, I know that when I have 0.125 liters of it, I also have 0.162 moles of that molecule. So my molarity is my moles per liter, which is equal to 0.162 divided by 0.125. Or 1.3 molar. Slightly out of order here because in our normal solution pathway we would have said volume times molarity is moles. Moles relates to moles. Moles, again, if we were just following this pathway, moles divided by molarity equals volume. Okay? That's what our pathway would have told us we needed to do. But in this case, we know moles, and we know the volume. We're trying to solve for molarity. So if I rearrange that equation to solve for molarity, it would be moles per liter, which is the definition we've been working with all along. Okay? So in much the same way we talked about the dilution problem, this is how the numbers play out. In the dilution problem, we figured out the volume of a known concentration that we needed, and we needed to change it to a new volume, which would reduce the concentration. Here, if I say I've got a certain amount of acid and a certain amount of base, the concentration, in this case, of the acid, what is the concentration of the acid? Well, I don't know, but I do know the concentration of the base. And I started with pure acid and a certain volume of base, and I drip the base into the acid until I get to the place where there is exactly the correct number of acid molecules to base molecules in the relationship here of 2 to 1. So when is this going to become a basic solution? When I have one more drop than when I have 2 acids for every 1 base. At that point, we've gone 1 drop too far. Actually, we've gone a part of a drop too far, right? Because if it's acidic and 1 drop later it's basic, somewhere in the middle there, it was neutral. Don't worry, 4 will not kill you. It'll be fine. So, by seeing where we start from, doing the titration, and then when we stop, when the solution changes because of the indicator and changes to be basic, we stop and we see how much base did I have to add to neutralize this. How much base did I have to add? That's this number. What was the concentration of that volume that I added? We know that. We were given that. So, that much of that concentration represents that many moles. And I know that the appropriate number of moles has just perfectly matched the appropriate amount of acid, and they relate 2 to 1, so I have twice as many moles of the acid. And I know that I started with this much acid. This much acid required this many moles. Okay, so what must its molarity be? And that's where we answer the question, what is the concentration of the acid? So every piece of this we've done before, just looking at it and driving it in a slightly different way. This is known as the pregnant pause. Full of potential. Let me just sit here for a second. I'm going to ask for questions in just a second, but I'm just giving you time to ruminate, to kind of base the moment in this new understanding. Yes, sir?
So what was the difference from what we did yesterday or the other days we did this?
The other days, what we've done every time has been, just speaking generically, if we use this kind of solution diagram, we've always driven from either a mass to a mass, or from a volume and a molarity to moles, and then to a mass. We've never done the upside down U. We've never gone up, across, and then back down again. Every time we've come down, across, and up, or up, across, and up, we've always ended with an up. This time with the titrations, we end down. So we're driving back towards a volume-molarity relationship. But see, the thing is, whether it's mass or volume and molarity, it's what we're actually doing is converting that into moles, right? If I have a certain mass, I divide by the molar mass to get the number of moles. If I have a certain volume, I multiply by the molarity to get the certain number of moles. Boom, now I'm in moles, I can use stoichiometry. I can relate them back and forth by the reaction equation because I'm actually relating pieces to pieces, not the volume of the pieces or the mass of the pieces, but the pieces. once I can relate the pieces to pieces and I translate that stoichiometrically from the amount of base using stoichiometry to the required amount of acid, well then now I'm working just with one molecule again. Working vertically, you're working always within that molecule. Every piece of information on here, for example, would relate to nitric acid. And every piece of information over here would relate to magnesium hydroxide. And I get to go between the two. The Rosetta Stone of understanding how to solve the problem is stoichiometry. But I can only cross over when I'm speaking the language of moles. I can't cross over speaking the language of mass or the language of volume. You can only do it with moles. And so every intermediate piece here, molar mass and molarity, gives us the way to translate from, for example, volumes to moles or mass to moles. So we're getting it into the language of moles, and then we can translate it over to the other molecule in question. Then using straight, if I also ask you a question about, and how many moles of magnesium nitrate would be produced? You go, oh, okay. How many moles of magnesium nitrate? Well, I've got moles here, and I can relate it over here, and it's a 1-to-1 relationship, so I must have produced 0.081 moles of magnesium nitrate. See that? And twice as many moles of water. So the same number of moles as the acid, that's how much water I produced. And if I asked you, well, what was the mass of that water? Well, you would say, well, that's easy. I've got the moles, and I need to multiply that by the molar mass to figure out the mass. Right? Because we're used to coming across and working up. But if I said, okay, you've got this much magnesium nitrate, and it happens to be in a solution of, with this volume, what's its molarity? That's the wrinkle. That's this piece right here. It's not that you haven't seen it before and that you can't understand it, it's just you've never thought about it in that way before. And they're so confident you'll get this, they don't even give you a example. How's that? But, because I am Mr. Baker the Benevolent, I know that's what you call me behind my back, right? Mr. Baker the Benevolent. No, what? Not a word you associate with me? Okay, that's fine. But anyway, let's go ahead and look at a practice problem that uses titration. Let's work it out together. Okay, for those of you that are taking notes, things will help you with your homework. All right. Give me just a moment. I'm going to see if this computer will actually wake up in the time we have left in class. I don't want me to play one of those videos. Windows is making me change my password, so that's easier.
That's fine.
We're doing titrations.
Really? Wow, I love titrations. I don't remember what a titration is.
I got to do chemistry last night. So
What? Titration? What?
See, that was not cerebral humor. That was pretty right out there. Okay, let me see if it starts up. Let's go ahead and start this problem and then. let's go ahead and take a look at practice problem number 9. Again, I'll just do it according to my technique, like I just described to you. So, a chemist needs to know the concentration of some sodium hydroxide that's in the laboratory. They say, hey, look at this. I found a bottle of sodium hydroxide. I wonder how strong it is. I wonder what its concentration is. Still loading. Okay. But I can't really use it till I know what I've got, right? It's some kind of sodium hydroxide. Is it okay? Is it safe? How am I going to use it? So I need to standardize it. I need to figure out how strong it is. So we get sodium hydroxide. To find out, she titrates 15 milliliters of hydrochloric acid. So we're going to be titrating hydrochloric acid and sodium hydroxide. Is that right? HCl plus NaOH produces H2O and NaCl. Ionic, it's going to be water and a salt. I've got a 1-to-1, produces 1. I'm left over with a sodium and a chlorine. Sodium is a column 1, chlorine is a column 7. They match 1-to-1. Boom, there's my balanced reaction equation. Okay. Now that I have the basic reaction, the balanced reaction equation, I'm going to go back to the problem and look for the particulars. Chemist needs to know the concentration of NaOH, titrating against HCl, boom, boom. Needs to know the concentration, so it's going to be here. The molarity of this is trying to find out the concentration of sodium hydroxide. She titrates 50 milliliters of the solution. 50 milliliters is 0.050 liters of the solution. With 3.5 molar HCl, if it takes 34.3 milliliters, also known as 0.034 liters, what's the concentration of the sodium hydroxide? So all the information is on the board. They're related on 1-to-1, right? Since I want to use stoichiometry to go from information about hydrochloric to information about sodium hydroxide, I need to use stoichiometry, which means I need to get to this point. I need to convert it into moles. So I go from volume, I use volume and molarity to get moles. Moles relate to moles 1-to-1, and then I have to figure out the molarity given the moles and the volume. Let's just walk the pathway. My number of moles is going to be my molarity times my volume. The number of moles, because up, remember, is multiplication. So it's going to be 0.3034 liters times 3.5. Molarity is moles per liter. Liters cancels liter, leaves me with moles. And so 3.5 times 0.34. Say again?
0.119.
0.119. So I have 0.119 moles of hydrochloric acid. If I take 0.034 liters at a 3.4 molarity, in that solution I will have 0.119 moles of hydrochloric acid. Now that I've got it in moles, I can branch from moles to moles. And I go moles to moles with a translation of 1-to-1. So factor is 1. So they're the same. Everybody sees that, hopefully, right?
Yep.
They're the same. So I have 0.119 moles of sodium hydroxide. Why? One molecule reacts to neutralize one molecule. 1 mole reacts to neutralize 1 mole. 0.119 moles reacts to neutralize 0.119 moles of that. I've got my moles and I have my volume. All I'm looking for is the molarity. Molarity is equal to moles per liter. In this case, it's 0.119 per 0.050. Moles per liter is my molarity.
$2.38.
2.3. So it's 3, if I wrote it that way, 3 and 3, the 3 sig figs. So 2.38. It's 2.38 molar. What's that mean? For every liter of my sodium hydroxide, there are 2.38 moles of sodium hydroxide. How do I know that? Because within 0.050 liters of sodium hydroxide, there are 0.119 moles of sodium hydroxide. And that's problem number 9. Volume times molarity to give me moles. Moles relate to moles. Moles divided by the volume gives me the molarity. They could equally have told you that does this titration and actually knows the molarity, how much would you anticipate would be required? Right? So if you had moles and you had molarity and you were looking for volume, what would you do?
Do what?
If you somehow knew the molarity and the moles, but you didn't know the volume, how would you figure out what you needed? I'm moving the pathway from here to here. How do we get here? It's this divided by this, right? Down is division. So if I knew this and this, I could compute this by taking moles divided by the molarity is the volume. Not given this, I need to know that it's moles divided by the volume gives me molarity.